solutions. The authors are Eike Schäffer, Fröhlig, Andreas Mayr and Jörg Franke. Please feel free to comment on the live chat on this YouTube stream on the right hand side, as you can see, and put your questions in there, and we will have Eike back on the phone after the next presentation. So we are looking to your next presentation, Eike.
A warm welcome. My name is Eike Schäffer of the Institute for Factory Automation and Production Systems of the Friedrich-Alexander-Universität Erlangen-Nürnberg, and I'm very proud to present our paper, A Method for Collaborative Knowledge Acquisition and Modeling Enabling the Development of a Knowledge-Based Configurator of Robot-Based Automation Solutions, in behalf of my colleagues. The paradigm of mass customization forces companies to offer products in numerous variants, providing proper solutions for individual customer requirements at the mass product price level. As the number of variants is increasing, configurators play an important role in tackling this challenge. One domain to meet individual customer requirements represents the planning of automation solution. In this domain, configurators promise a higher potential for efficiency increasing amongst manufacturers and system integrators. Of complexity of a system such a robot cell highly depends on the number of elements and relationships, and often exceeds the complexity of the respective product, especially with regard to the complete automation solution. In addition, a robot-based automation solution combines the expertise of different engineering disciplines such as mechanics, electric, pneumatics, and software. In the conventional planning of such solutions, the collaboration of these experts is necessary. It is typically organized by a project manager with a significant amount of coordination work. The conventional planning process involves implicit knowledge, a dynamic, time-consuming response to long disregarding constraints, and independencies often resulting in so-called firefighting. To enable the development of a web-based robot configurator, and in order to benefit from the advantages of configurators, a method is needed to enable a simple and scalable development of the underlying logical configuration model, also allowing for a division of labor. So far, many knowledge-based projects are conceptualized by individuals or small groups. However, there is a lack of a procedure for the collaborative work on knowledge acquisition and modeling, especially for multidisciplinary configuration projects for mechatronic solutions such as a robot-based automation system. By transferring interdisciplinary knowledge about the planning of robot-based automation solution in an explicit configuration model, advantages of so-called knowledge-based systems can be realized. The term knowledge-based system is often used interchangeable with expert system, where the latter particularly refers to the capturing of a human expert's knowledge. In contrast to the human expert, the expertise is available with a constant performance, condensed, permanently, locally unbound, and immediately. This saves time and money and improves the quality and scalability when planning automation solution. However, in order to create such a configuration model, the expert knowledge must be found, extracted, pre-processed, standardized, and condensed. It is one, if not the most difficult task in creating a knowledge-based configurator. In general, configuration is a special case of design activity where the artifact being configured is assembled from instances of a fixed set of well-defined component types, and components interact with each other in predefined ways. Among the other configuration tasks can be handled with three approaches: tabular, rule-based, and constraint-based. Tabular is a list of all the valid combination of components, though no configuration system is needed, but the maintenance effort is very high. As an example, with just 7 robots, 4 adapter plates, and 4 gripper, 112 variations are possible. But only 11 of these configurations or variations are correct. Existing alternatives to configurators are classical lists in Excel, where all alternative configurations are manually stored, hard-coded programming solutions, which include implicitly the expert knowledge, existing enterprise software, which is indirectly used for configuration, or the classical manual planning process without software support. Another approach is the rule-based approach, with production rules determining which components may be combined. It is easy to derive from natural language, but the maintenance effort is also higher than the constraint-based approach. Also, this approach gets very complicated to maintain with a higher number of rules. Out of these, the constraint-based configuration allows a model-based component-independent representation representation of the required configuration knowledge and is most scalable. Due to the model-based approach, the constraint-based configuration is used in the following concept. Existing methods for the development of configuration model alternate phases of individual work with joint workshops in order to synchronize the results, but are primarily developed by a central person. In addition, these methods are tailored for simple product configuration showing deficits in standardization and the creation of reusable, scalable knowledge elements. With special regards to interdisciplinary and collaborative work, further standardization is necessary. The method consists of 8 consecutive steps, which can be delegated to different employees due to their modular structure. The first 7 steps are executed sequentially in order to develop an appropriate configuration model. The last step also addresses a continuous refinement of the model by touching contents of all previous steps. While the method is generally applicable, it is explained using the example of a robot-based automation solution. The 8 steps serve as an agenda for the following presentation. In general, configuration offers a great potential but also requires a high initial effort and is only understood by a few people. That is why the first step, economically relevant use cases that are suitable for being mapped into a configuration have to be identified. The selection of a suitable use case is decisive for whether quick success can be achieved. For small and medium-sized enterprises, SMEs with fewer than 50 employees, only 1 in 5, and SMEs with fewer than 250 employees, only 1 in 3 use industrial robots for handling systems in production at all. Based on the market statistics, robot-based automation solutions for SMEs are identified with high demand and potential. In addition, half of the robotics systems in production are used for handling application. Following the Pareto principle, the focus of the aspired configurator for robot-based automation solution is set on the frequently occurring handling and then assembling scenarios, since robot-based welding is usually much more complex. The clear definition of an economical viable use case makes it easier for the management to release the necessary resources for the creation of the aspired configurator. Looking at the phases of the factory planning, the planning of robot-based automation solution addressed here can be classified in the area of Roth planning and more precisely within the ideal planning phase. The ideal planning phase is characterized by 3 main steps. Firstly, the function and task determination of the whole production system and its individual resources. Secondly, the dimensioning of the resources. And thirdly, the structured positioning in the ideal layout. In the second step, best practice, i.e. successfully implemented robot-based automation solutions, are collected. These solutions serve as a knowledge base for the next step, as they contain implicit information about practical proven implementations verified by real operation conditions. In addition, best practice provide initial parameters for effort-reduced modification configuration. Documents such as specification, technical documentation, and existing digital models provide these data, especially for facilities that do not have a large number of self-implemented automation solutions. This step represents a major challenge. Many system integrators regard the release of such information as very business critical. Only for sales support purpose a transfer is conceivable, according to our expert discussion at the Automatica 2018, the lead exhibition for smart automation and robotics in Munich. This challenge can be avoided via strategic cooperation with a system integrator, respectively domain expert. To ensure the transferability and scalability of the knowledge base, they should be based on a generic model and a norm description language. Therefore, the so-called SPPR model is introduced as a generic semantic model for describing production systems. As can be seen, the configuration model for robot-based automation cells includes scenario, product, and process as an input and the technical implementation itself resource as an output. This scenario containing general conditions and structural topological information for the automation cell. Serving as a starting base, it decreases the time required during configuration and limits the mathematical complexity for the solver. The product represents the objects and their different processing stages. The properties of the product set the requirements for the resources which execute the processes. The processes define the task for the resources and are used according to the standards such as VDE 2860 for handling and the DIN 8580 for the further operations. In addition to the user requirements, i.e. scenario, product, and process, the configuration solution represented by a set of resources is also included in the semantic model. The solution has a placeholder structured consisting of generic resource modules that can be instantiated as required by the given task. In the third step, step, abstract. Generic topological elements are extracted from the best practices and information out of expert interviews and literature. All the elements needed for modeling the automation solution should be found in a so-called 150% topology. The SPPR model is represented in a 150% topology. Topological elements are not only physical objects that are required in a robot-based automation cell to perform the manufacturing tasks, i.e. resources, but also general concepts involved in the planning process, such as manufacturing processes, product information, the surrounding area, management, objects, or human interaction. By gathering the different topology elements, the 150% topology is developed as a condensed general structure. Here, the 150% topology can be seen and used for further configuration projects. The presented method focuses on the demand-oriented modeling approach where the data schema is based on the needs of logical queries. In particular, step 3 and 4 outline the primary challenge in the development of configurators, as these contain the condensed expert knowledge. In the presented cases, dependency knowledge between the elements is derived in the form of constraints. For this, a selection of use case relevant elements is extracted out of the 150% topology. In doing so, a two-dimensional assignment matrix is created holding all relevant topology elements on each axis. Each field of the matrix represents a binary relationship of the two affected elements. The matrix arrangement enables the sequential collection of the constraints in a well-defined workflow. Due to the standardized structure, several people or small groups can work together in a workshop in parallel. When assigning matrix elements, the knowledge engineer considers knowledge and strength of the persons available and involved, so the acquisition can be carried out based on the division of labor, like an expert for robots. In addition, white knowledge spots come explicitly visible through the matrix arrangement. This also enables the structured reuse of individual knowledge elements, respectively constrained from one configuration project to another. Missing expertise can be obtained through literature screening, expert interviews, or outsourcing. This way, the knowledge base can become extremely rich in content. Moreover, the detail level of the configuration can be easily adjusted by the number and the depths of constraints of a field. By the structured completion of a field of the matrix, all possible relations between the topological elements are considered. Based on the extracted constraints, it becomes obvious which logical attributes the given elements require in order to be executed automatically within a configuration framework. In order to be able to accomplish the knowledge acquisition process in a more structured and standardized way, a tool is evolved which primarily supports the steps 3 to 5 of the aforementioned method. The main purpose of the tool is to enable experts to formulate standardized constraints representing the primary configuration knowledge. In this way, the expert can semantically formalize his unstructured knowledge into a constraint via predefined elements and attributes. This enables the demand-oriented building of configuration models containing only required elements and attributes. Based on existing topological elements and their attributes, rules can be formulated and connected to queries. So there are two ways. One, you start with the existing topology and formulate rules and queries, or no topology is existing, then you formulate first rules and questions and use them to build up a topology. The tool supports the structured collection of scenario, objects, attributes, rules, and questions. The last three steps of the method addresses the integration and implementation in a configuration framework. In the sixth step, topology elements and their attributes data schema are transferred into the specific configuration language. Based on these, the constraints from the fourth step are added to the model referring to the element's attribute. The constraints are translated into machine-readable language given by the selected constraint-based configuration framework. For this process, the Tecton configurator and engine was used. In the seventh step, concrete components such as specific robots or grippers are instantiated based on the data schema. In doing so, the components must be transferred to a generic manufacturer-independent description. In the eighth step, the configuration model is tested and improved iteratively. For this purpose, the best practices are initially used to extract the underlying constraints. By entering product and process specification in the configurator, a solution, i.e. matching set of resources, is generated. Based on a possible discrepancy between configuration and best practices, further constraints can be derived. In this way, the configuration results gradually adapts to the real implementation. The presented approach consists of 8 consecutive steps, enabling the creation of an interdisciplinary, more standardized configuration model and a division of labor. First, use cases and best practices are collected. Out of these, elements are extracted. Using these elements, constraints and attributes are formulated and integrated into a configuration framework. Out of these, they can be refined and reused for future projects. By using a support tool, this approach is supported in a more standardized way. Thank you for your attention. attention and to the Federal Ministry for Economic Affairs and Energy for supporting Robotop along the technology program PACE. Do you have further questions?
Thank you, Eike, for your presentation. For those of you who has just turned in during this presentation, this is the second live stream of the CIRPe Global Web Conference 2019. As next, we plan to have a live discussion with our presenting author, Eike Schäffer, from the laboratory of Jörg Franke from University of Erlangen. Eike, are you online? Can you hear me?
Yes, I hear you.
Great. We have received 2 questions regarding your presentation. The first one is, what are the problems with general concept planning for robot-based automation solutions, especially for small and medium-sized companies? Could you comment on that, please?
Yeah, thank you for your question. It's a very interesting question. Like, if you go to the Automatica, you have 2 kinds of companies who are there. You have, at the one hand, the component suppliers like Scha, KUKA and Co. who sell the components, and then you have the system integrator who combine these components. And for the system integrator, you have huge companies who build like specialized engineering tools. But there is really no tool between for the calm SME to build automation solutions, because all tools are highly specialized and therefore only usable for like system integrators. And like, if you want a configuration solution for a small or medium-sized company, they don't have the highly expertized knowledge. So they know how to produce their product and they know their processes, but they have no idea about automation solution. And if they go to the exhibitions and then they see just, hey, buy a robot, buy a gripper and put them together, but it's not so simple. So to get it easier to them, you need like some guidance who, like, if you buy a car, takes them by the hand and then asks them only questions they can answer. So if you go to a car dealer, nobody would ask you like which screw size you want to use for your car. But if you buy an automation solution, sometimes people ask you so specific knowledge you can't answer because you're not the expert for this. And so this was the aim for the configurator, just to ask questions you can answer and map these questions in the logic behind to the technical solution. So you don't have to choose what you need because you don't know it. So you just answer what the process and the product is you want to produce.
Yeah, we're listening to you. Sorry.
Yes. That's all to this point.
Okay. Do you see, I mean, of course it's an industrial challenge for, especially for small enterprises also to invest in such new tools. Do you have any approach which can be used easily or implemented easily in an industrial environment, or are you working on it?
Yes, thank you for your answer. Just mention the picture shown in the live stream is not me. And
sorry for the mistake. We just corrected it. You are going to see it in a second.
Yes, and to the question, yes, we are doing it. I can just post the link also in the live stream. We're a government-funded research project, and at the moment we have some live demonstrators which can be seen at the Automatica 2020. There we will be at the exhibition stand for the Bundeswirtschaftsministerium, and there you can test the tools when we want to address also a huge audience. And there we make a lot of user tests. So we developed on the one hand user-centered prototypes to test it with end users. And on the other hand, we discussed with a lot of system integrators and experts to combine this knowledge and like to make a lot of field tests for usability, for configuration, integration. And we have a running system, but at the moment it's just a closed beta testing, so it's only for the project involved participants. But if you want to have more information, I just posted in the live chat, we have a homepage where you can find further information to the research project.
That would be great. It would be great if you could post your web link for the project, as well as if you have any information about your exhibition next year, that our audience can follow the next steps on this approach. The next question regarding your paper was about the future work. Actually, you mentioned that you would like to simplify the 8 steps you just presented. Could you detail how would you like to combine them, or would you like to simplify them for which purpose?
Okay, for the first step, like simplification is necessary because we want more explicit work sharing. So at the moment, you have some experts who have, I say, the God brain, who have to know it all. But like to get better scalability, you have to have better work separation. So one aspect to make it easier is to develop specific tools like Excel tools for start, and then make them like with Java or other higher concepts. So you are guided through the process. Also, you can use like BPMN 2.0, also business process modeling and notation, to model the workflow and make it automatically runnable. And also, we are building at the moment templates. So if you are doing some specific task for this process, you just can fill out the templates and don't have to think about the structure. Mm-hmm. And the last step is like we built like some semantical models in the background. So to get further standardization into naming and other stuff. So for this, we have also a paper which is ongoing at the moment.
That's great. So we are going to follow your next publications and we'll learn more about the simplification. Thank you, Eike, for your time, and hope to see you soon.
Thank you.
Bye.